So, welcome everyone. I'm presenting today on solid polymer electrolytes for structural energy storage applications and other applications as well. My whole PhD was pretty much on this topic, so hopefully I don't bore you with the journey, but I'll cover a fair few papers and a fair few different sub-projects here and some branches where we sort of branched out into other areas. So, you obviously are fairly familiar with structural energy storage, but basically the whole pitch of it is combining load bearing with energy storage in one structure with the aim of increasing efficiency and reducing mass of the overall structure. So, obviously, you know all about this, but you take a carbon fiber car or car with carbon fiber components, and the whole pitch is that you integrate not as an addition to these components, but as these components, basically structural energy storage panels, saving mass overall rather than having a separate battery. And in a composite, this is the research group I work in is a composites research group. So we work in mainly composite capacitors, and this is basically what it looks like: is two layers of carbon fiber that are conductive and they act as conductive electrodes, and then this is held apart by a glass fiber or other fiber separator. And this whole system is held together by a biphasic or bicontinuous, so two-phase solid polymer electrolyte, and that really is where my whole project has been focused on optimizing. So I wonder if I can, I don't know if I can actually do my little mouse thing on PowerPoint here. But if I did have my mouse, I'd point at the carbon fiber and I'd say sort of, so most of the research group I'm in, which is the Luke Henderson research group at Deakin University, has focused on functionalizing carbon fiber. So they're looking at the interface, mostly functionalization with electrochemistry. So putting, in the case of energy storage, redox active functional groups on that surface, or functional groups that actually are covalently bonded to the carbon fiber. So going a step further than purely a sizing on the carbon fiber, which is obviously just a physical deposition, going to the point of actually a covalent bond with the carbon fiber. And there's many papers that Luke has done on that topic, and some of them have been focused on energy storage and some of them have been focused on purely improving mechanical properties in the matrix and obviously increasing interfacial shear strength. So this is what a solid polymer electrolyte looks like under a scanning electron microscope. You can see the porous network, and basically within this porous network is where the liquid electrolyte sits. To actually look at this under a scanning electron microscope is pretty complex. Sometimes the biphasic structure collapses when you remove the electrolyte out of the system, sometimes it doesn't, and scanning electron microscopes are not very compatible with most ionic liquids, so we normally have to remove the ionic liquid from the system, which is a bit of a logistical challenge to visualize what's going on there. So at a lab scale, this is what our prototype capacitor devices look like. We're seeing this from the top view. Basically, we've got a 3 by 3 centimeter carbon fiber electrode on the top, connected to a copper current collector, and then we've got our glass fiber filter paper separator. This is obviously prototype scale, but very small scale because we're using obviously more expensive reagents and obviously doing a lot of repeats, so we want to keep it as small as possible, so we're reducing costs and being as environmental as possible. And these are quite flexible, but obviously they'd be embedded within a more solid matrix if they were applied in a composite. So solvate ionic liquids are a key part of the electrolytes in most of the systems that we've applied. They're obviously a subclass of ionic liquids, as you can tell by their name. As with the rest of ionic liquids, they're thermally stable, non-flammable and conductive electrolytes. They're a three-part ionic liquid, so they consist of a lithium salt that is dissolved and chelated by an ether ligand. And basically the ether ligand solubilizes and diffuses the charge on the lithium cation. In the case of most of our salts are lithium. And then the anion has quite a diffuse charge, so it's a kind of pseudo spectator in these systems, but the anion does have a big effect. So some of the earlier work that I did in my honours year was kind of more focused on ligand optimization, and then my later work has been focused on anion optimization. So the key part of these three-part systems is they are modular and tunable. So you can change out the ether ligands for the G3 ligand, which is obviously fitting that lithium cation pretty perfectly. It's obviously the same size as a crown ether for a lithium if it was a closed crown ether. And then the G4 ligand obviously has that one extra arm, so it's a bit looser chelation. So you'll see in literature that these have been applied with various different metal salts, metal cations, and you can apply a variety of different anions in these systems. So my research has been focused on the G4 tetraglyme ligand, the G3 triglyme ligand, the lithium cation, the TFSI anion, and the FSI anion. I've kind of covered the differences in the ligands, but the differences in the anions is basically that TFSI has a CF3 group on the end, where the FSI just has a single fluorine. So obviously, I mean, you can see the spatial diagrams over there on the right. The FSI is a bit more bulky, but there's obviously pros and cons of how much charge is held on that nitrogen atom and where the resonance stabilization is in terms of the charge, which obviously has quite an effect on the macro level properties of these systems when they're applied in electrolytes. So going into my work, and this was basically in my honours year, which was 2023, a while ago now, the lithium G3 ligand with the TFSI anion was the benchmark applied in literature. This was what had been applied in structural capacitor devices by one of my supervisors, Dr. Baghir Masiri, and this was kind of our benchmark. This was where we were working from. Going into this work, we had a few hypotheses. The first was that the G4 ligand, which hadn't been applied in capacitor devices or, well, structural energy storage before. So there was a hypothesis that G4 could result in higher conductivity systems, as G4 chelates the lithium cation less strongly and allows the lithium to accelerate faster than the other Solvate ionic liquid components. And we see this happening a lot at higher temperatures. So a lot of my early work in my honours year was focused on how these systems performed in self-diffusion, so it was very physical chemistry focused, how they would diffuse at elevated temperatures. And we were really pitching this at sort of thinking about a capacitor that was applied, for example, in an electric vehicle in an uncooled capability where it would be operating between 60 and 80 degrees Celsius. And obviously, this is one of the advantages of using an ionic liquid, is that they're stable at that temperature, whereas traditional electrolytes are not necessarily stable at higher temperatures. The second hypothesis was that the FSI anion could result in lower viscosity systems due to the reduced anion bulkiness. So in my honours year, I probed these systems through diffusion NMR. These systems are really great because you've got hydrogens on the ether ligands that you can track through diffusion NMR, and the lithium cation, which does a great signal on diffusion nuclear magnetic resonance NMR spectroscopy. And obviously you've got the fluorines on the anion. So you've almost got an easy way to track all three components. Of course, in saying that, I think I spent 5 to 6 weeks of my honours year doing diffusion nuclear magnetic resonance spectroscopy. So it may be more easy in theory, I will note. But I spent a lot of time doing diffusion NMR in that year. So just throughout this presentation, actually I think I might have actually changed it a little bit towards the end, but sorry. Most of my presentation is this sort of sample labeling, and I've kept the sample labels in there, but they're a little bit small. So if you kind of remember this color coding, then it keeps things a bit more simple. So I will get to solid polymer electrolytes too, by the way. This is just a bit of background. So basically, this is what the lithium diffusion looks like in a TFSI system. And of course, this obviously has effect on bulk conductivity, which is what we were interested in. And you can really see the lithium exponential acceleration as it reaches 80 degrees there. And this is obviously, as I said, purely chelation dynamics driven. But what happens when you look at the FSI system? So you can see the FSI systems, the G4 is actually going slower than the G3 TFSI at 80 degrees Celsius. So there's a vastly different relationship. You see a different pattern at room temperature where the G4 FSI has higher conductivity than the G4 TFSI. but vastly different relationship at a higher temperature, which is really interesting. So this is chelation dynamics driven. Obviously, the G4 ligand lithium is still moving faster than the G3, but it is also driven by anion electron charge density dynamics of how much that lithium cation is interacting with the anion as it self-diffuses through the solution. And you can kind of get a bit of a debatable grasp on this depending on whether you look at the molecular orbitals and orbital overlaps on this, but there definitely is a change in where the negative electron density is held in the different anions, and obviously that's having an effect. So I'll just summarizing, lithium diffusion properties are dominated by both charge density of the anion and chelation strength of the ligand. So the viscosity of these systems measured through rheology is obviously effectively the inverse of conductivity and diffusion pretty much. So we see an exponential thinning behavior as it increases in temperature. And you can see over here on the right, this is with some super concentrated lithium electrolyte. So I think the one on the far right is actually at a 1:2 concentration of, basically you've got double the molar ratio of the lithium salt in there, and it is very viscous in this sort of upturned jar test. Viscosity at a high temperature is a little bit different to viscosity at a lower temperature. So we see that the tighter chelation of the ligand and the anion with and the more bulky TFSI anion with the G3 results in higher viscosity, obviously. And this was a lot of basically what we did was probing what I did was probing the structural property relationships of what was going on here. So the TFSI anion had greater viscosity than the FSI anion for each ligand type. And this was obviously due to what I've already explained previously. It's basically the inverse of conductivity and diffusion. So I measured conductivity through electroimpedance spectroscopy, basically measuring resistivity and then calculating the inverse of that. And this is pretty simple, that basically because there's an inverse relationship, the little light blue line that you can see there that has higher resistivity on the x-axis, that corresponds to lower conductivity, whereas the white line that has lower resistivity has higher conductivity. Sorry, I just jumped ahead with my own explanation there in my slides. So at room temperature, basically, you can see the optimization here. So the light blue is what we started with, and that was what we were applying in our devices. The green was basically the optimization that happened in my honours year in the first paper of my PhD, and the red and the white is a paper that we're still working on now. We've got some collaborators over at Michigan State University who are just writing another segment on that, but hopefully we'll be submitting that towards the second half of the year. But you can see that optimization in terms of conductivity, that we've moved from below 1 to almost 2.2-ish in terms of conductivity in millisiemens per centimeter. So that's obviously a big pitch in terms of my PhD, was that we went through from physical chemistry of seeing whether you measured something in conductivity and diffusion, if that was going to be better, did that actually result in improved properties in solid polymer electrolytes, and did that follow through to improve properties in capacitor devices? And we really wanted to see that full flow through, because I always see it as a little bit pointless if you're doing optimization of electrolytes in purely physical chemistry, but you're never actually applying them in energy storage devices to actually evaluate if they actually work and how stable they are, particularly cycling stability, for example, tells you a lot about how stable an electrolyte is. And a good example of that is that even though I'll show this later on, but even though the G4 FSI electrolyte has the greatest conductivity at room temperature, it actually doesn't have the highest performance in a device when you're cycling it a lot. And the G3 FSI electrolyte, which I guess is a combination of the best of both worlds in some way, the tighter ether ligand, so you've got greater stability, and the FSI anion, so you've got reduced viscosity and higher conductivity, that actually performs better because it's more stable. So here's conductivity measured over a temperature ramp. pretty much shows what you'd expect. Nothing really groundbreaking here. Coming back to the solid polymer electrolytes, these are two phases. So one mechanical solid phase and one electrochemical liquid phase. So I measure mechanical properties in these systems through flexural 3-point bend testing. One of the big issues that I see in the literature is measuring mechanical properties, well, perceived mechanical properties, I will say, as storage and loss modulus on rheology. And that's a big issue in solid polymer electrolytes. They are flow properties, rheological flow properties of a liquid, and are not actually mechanical properties. So I always encourage collaborators to send me samples if they want some actual mechanical properties, because unless you're addressing the mechanical properties of basically the flex of your composite in a flexural direction, then storage and loss modulus is kind of irrelevant. You've just proved that it isn't flowing anymore. You're not actually showing the mechanical properties. So that's just a bit of a debate that I often have at conferences. And I measure the electrochemical properties of these systems through electroimpedance spectroscopy testing, EIS, and you can see here the little 1 centimeter by 1 centimeter little solid polymer electrolyte sample is sandwiched within a battery testing clip. So just coming back to, I'll get back onto solid polymer electrolytes, but one of the challenges and benefits of these systems, and this is probably, you might have already heard of this with your, Christopher mentioned about the work you do on additives and curings for epoxy resins, for example. Solvate Ionic liquids cure epoxy resin with amine hardeners, and they, catalytically accelerate the curing of epoxy resin systems with amine hardeners. And this changes with the type and configuration of the Solvate Ionic liquid. And I actually went on to use this information to apply. Previously we'd used the G3 TFSI in capacitors, and that's got around a 60% reduction in gel point. You can see the graph on the right here, that red, the first red data point there is at a 1-to-1 ratio, molar ratio. And I actually went on to recommend using the G4 TFSI because it had much better properties of obviously allowing a little bit more degassing and a little bit more working time, and because the G3 one, you basically mix it, you start feeling it heating up in your hand as you're mixing the container, and you don't have much working time to get that into your vacuum assisted resin transfer setup, basically to vacuum infuse your composite. So I'll mention it later on. There is a slide where basically the G4 TFSI 1-to-1 ratio electrolyte was applied in a structural battery setup, and this obviously was measured with rheology. So coming back to the solid polymer electrolytes, these plots are what I live and die by for my PhD. I was obviously trying to move across and to the right of improving conductivity while improving mechanical properties. You can see here that the high viscosity systems result in higher mechanical properties. So that G3 TFSI system that has the greatest, more bulky anion, the greatest chelation of the lithium by the ether ligand, that has 4 times the mechanical properties of the least viscous system. And then obviously the inverse of this is the case with electrochemical properties, but there's a little bit more of a magnitude change with around a 9 times difference. And obviously understanding this trade-off was something that really influenced our choice of electrolytes. And it's something that when I talk about resin optimization later on, where we kind of stuck with a particular electrolyte as a benchmark, we potentially will apply in the future our optimized resin with our optimized electrolyte and see if we get, I guess, the best of both worlds, hopefully, and improved properties. And you can see here the error bars that are in here really reflect the issues that we have with not being able to, well, this is the trade-off of the catalytic curing, because we can't degas these systems before putting them into a mold, which is a bit challenging and obviously introduces error. I'll talk about that a bit more with some UV 3D printing where we got around that issue. So just coming back to the prototype devices. So this was the benchmark applied in literature. This is an unfunctionalized, de-sized carbon fiber, so basically plain carbon fiber interacting with a G3 TFSI electrolyte in a carbon fiber capacitor device. In my first generation of optimization, basically just looking at the ligand with the G4 ligand, we achieved a 25% improvement. So if we actually went back up to, I won't do it now because it'll make you dizzy, but if I went back up to my slides with the solid polymer electrolytes and the conductivity of the pure systems, the G4 TFSI was always performing better than the G3 TFSI. And we saw that in diffusion, we saw that in a lot of basically following from the physical chemistry, pure systems, through to the solid polymer electrolytes, and now we see it actually applied in the actual device performance. But I will note that in diffusion we see in the pure systems it's around 2 times, or sort of 2 to 3 times, and then in the solid polymer electrolytes you might see a 1.5 times increase, and then when you actually get it to applying it in the actual device you get around a 25% increase in performance. So it's something that I think was a really important takeaway from my project, that even though obviously an incremental increase in performance in a pure system is great, but there's a lot of factors that come into play and a lot of complexity in a prototype device actual performance, and you obviously have a lot the handing down of that performance to the actual end application is reduced compared to where you're up higher in the pipeline in the pure systems. So this was pretty cool. When we looked at the FSI systems, which was sort of a year halfway into my PhD, but has dragged out a bit more because they were a bit more complicated than anticipated. Well, complicated in a good way, which is great. We actually got up to 160% improvement in the capacitance, which is pretty cool. So I hope to actually apply this in the future with our prototype energy storage devices that have functionalized carbon fiber. So some of what one of my supervisors, Dr. Baghi Damasiri, has done is actually been modifying the carbon fiber with redox active functional groups, and then also depositing Maxine nanomaterials on those to increase the pseudocapacitance basically, or increase the surface area of the carbon fiber. I'd love to see how these prototype optimized electrolytes would actually go in and perform in a best case scenario of sort of the best of both worlds. So coming back to the solid polymer electrolytes, early on in my PhD I had a lot not working, and I came up with this side project idea that basically we should look into recyclability of these solid polymer electrolytes. And obviously there's many pictures around this of sort of, circular economy action plans, and there's a lot of incentive and drive for this from industry and government. So one of the key parts that I looked at conceptually early on was that these are two-phase bicontinuous solid polymer electrolytes. So conceptually they're a liquid trapped within a solid. And I had this very simple idea that surely if we basically macerated or broke up that solid, we could release the liquid and recover the liquid from these systems. And initially we did this purely by looking at the matrix without the carbon fiber, because we sort of thought, okay, the carbon fiber can be recovered separately and might sort of complicate the picture. So I published a paper on this that basically was about 6 weeks work, which was great. And basically I went to our local electronics retailer, which was just down the road from the university, and got a NutriBullet fruit blender, and basically used that for the whole project, which was pretty cool. So basically we took the electrolyte, blended it, then vacuum filtered it, and then removed some ethanol, which we'd used basically just to pretty much so the blender wouldn't clog up. It really wasn't solubilizing much. It was just so the blender wouldn't clog up. So then we removed ethanol from the solution. Ionic liquids love water, so then we removed any residual water at a lower vacuum point, and this was what we were left with. And that little blue tint there is a little bit of the amine hardener dye left in there in the ionic liquid. It only showed up in the visible spectrum. It didn't show up on infrared or nuclear magnetic resonance spectroscopy. And I did this once and I recovered over 70% of the electrolyte that was put in to the cycle. And I was so pleased about this. I went and told my boss, and my boss gave me a bit of a hard quest because he said, well, is this a fluke and can you do it 5 times? So I went back to the lab. I made up more electrolyte than I'd ever made before. And I repeated it 5 times and obviously got a great average result of around 88% recovery. But we didn't want to stop there. We wanted to also measure other inputs into the system. So we recovered 83% of the ethanol put into the system. And then we had this blended resin pulp, which had excess mass. So clearly, if we blended more efficiently or for longer, then maybe we would have reduced that a bit. But this excess mass was clearly where the ionic liquid was going, and we didn't really want to stop there. We sort of thought, okay, we've got this blended resin pulp. What do we do with it? So we came up with this idea that we could put it in as a binding agent in epoxy resin, and we got some great flexural mechanical properties showing that it didn't significantly reduce the properties. In fact, slightly improved them, although not significantly. Just as a 10 weight % filler. So we sort of showed that the leftover side product of this recycling process could actually be applied in a circular economy context, which was pretty cool. We probed the mechanism of why this was a bit stronger, and great SEM images from one of my supervisors there. But basically the resin pulp, the hypothesis was that the resin pulp was acting as a reinforcing agent, deflecting cracks. So coming to UV 3D printing of solar polymer electrolytes. So as I said previously, that catalytic curing was an advantage because we could cure things fast in the epoxy resin systems with the Solvate ionic liquids, but it was a big disadvantage as well because we had very little working time with the system. We couldn't degas the system. We had issues with homogeneity in mixing, and there are obviously various challenges. So we decided at one point to switch to a UV cured system, which wasn't there was no catalytic effect in the Solvate ionic liquid. So we mixed it with a Tinky Mixer high shear mixing setup, which improved homogeneity. And these are some samples over here being cured under a UV light. And we use basically an off-the-market UV 3D printer, unmodified, which was pretty cool. And we did the full spectrum of conductivity and mechanical properties of compression, tensile, and flexural properties. And you can see here in the conductivity, the different ratios here are the content of Solvate ionic liquid to resin. So obviously where you've got less Solvate ionic liquid, you've got less of a conductive phase. So you can see that the conductivity is far reduced, whereas when you've got that 80% of the ionic liquid, it's much more conductive. And of course, the opposite of that is true when you look at the mechanical properties, where when you've got the greater amount of ionic liquid, you've got far reduced mechanical properties. So this plot over here shows some of the optimization in these systems, particularly around reducing error and variation. So all of these 3 data points have error bars on them. It's just that some of them are quite small. So basically what we were working with from the get-go was the little star symbol, which was the ionic liquid basically mixed with an epoxy resin in a little paper cup and cured in a mold. Then we moved to curing the UV resin in a mold, and that's the little triangle data point. And when we actually cured line by line in 3D printing, we actually got greater mechanical properties and conductivity. So this was really great to see because we were moving in the right direction of sort of up and across in that conductivity mechanical properties plot, which is really great to see. We also created in this paper a Lego inspired capacitor device. I will say that the mechanical properties of this were a little bit sketchy because basically it fitted together rather than was cured together between the two plies. But we were trying to see if we could 3D print directly onto carbon fiber and apply that in a capacitor device, and we got it cycling, which was pretty cool. So there have been a few side steps in our journey. I made electrolytes for a application done by peers in Maxine functionalized capacitor devices. As I mentioned previously, the G4 TFSI electrolyte has been applied in structural batteries by James Randall. I also have done a little bit of work on corrosion inhibition and tribological properties of solvate ionic liquids. This was just in the pure systems. We are yet to, and I will hopefully get time eventually, to investigate the tribological properties of the solid polymer electrolytes, because of course, if this reduces friction in its pure form, imagine how it would perform if you've got a solid polymer electrolyte that is under friction, and theoretically you've already got a lubricating system actually trapped within that porous network. It's kind of a good pitch already, isn't it? But basically these solvate ionic liquids reduce corrosion under acidic environments, which is pretty cool. And we confirm this through corrosion weight loss testing and also electroimpedance spectroscopy, electrochemical testing. So there's been a bit of a sidestep as well in the journey around piezoelectrics. So we applied the G3 TFSI solvate ionic liquid and solid polymer electrolyte in piezoelectric systems, and this was at a 1 to 1.5 molar ratio, so with a super concentration of lithium TFSI. And a key finding of this was that solvate ionic liquids are piezoelectric, however, it is to a much lower degree than traditional ionic liquids. As I mentioned in that 3D printing paper, we actually also did some piezoelectric testing on the 3D printed samples and proved that they were also piezoelectric, which was pretty cool. Please check out our latest review paper on solvate ionic liquids. This came out last year, and I've received some great feedback on how valuable it's been for some people. I will also extend a credit to Jean Simon, who did most of the figures in this paper and who is a whiz on Blender. That's where all these fantastic figures came from. Just coming back to different salts. So we initially tried to apply zinc solvate ionic liquids in solid polymer electrolytes. However, zinc, because it has that 2+ charge, requires a super ratio of the ether ligand to make it dissolve and be a solvate ionic liquid. So I think it's around a 1 to 1.5 ratio. So 1.5 times the amount of the ether ligand to 1 for the zinc. And this was a bit challenging because we couldn't actually apply this it wouldn't cure in our solid polymer electrolyte. So it was great that it was a solvate ionic liquid, but if it wasn't actually relevant to our application and wouldn't cure, then what was the point? So we kind of went back to the drawing board, and one of my supervisors, Baggy Damasiri, came up with the idea to basically use a traditional electrolyte of basically just zinc salt in propylene carbonate and solvent, I should say, and use that with the UV cured resin. And yeah, we got some great results. This has been applied in some structural batteries, and I did the solid polymer electrolyte part of this paper. And as you can see here, the zinc traditional electrolyte basically is, because it has much lower viscosity, it's not an ionic liquid, so it doesn't obviously have all the advantages of thermal stability of an ionic liquid, but its conductivity is through the roof. Mechanical properties aren't bad, and obviously it was using something that wasn't lithium, which was great. Just recapping that throughout my PhD, I've done a fair bit that wasn't my PhD. So back in June 2025, I actually got the opportunity to address the UN. In April 2025, I represented Australia at the Global Disability Summit and also represented Australia in Fiji in October 2025. I presently have 4 board roles, one of which is on the board of the Royal Australian Chemical Institute and on 2 public sector Victorian state government boards. I serve on various committees for the Molten Salts and Ionic Liquids Discussion Group for the Royal Society of Chemistry. Until recently, I was also on the American Chemical Society Australia Chapter Committee, but I had to get off that because I was a bit too busy. But I'm the newsletter editor for the Molten Salts and Ionic Liquids Discussion Group, and I also serve on committees for the International Younger Chemists Network. And with all this on, I still submitted my PhD thesis in March 2026 at the 2.25 year mark, which is a bit of a race to the finish. I'd like to acknowledge my supervisors and many people who obviously made this possible.